Hello everyone, let's talk about another medium problem on Leetcode today. Find the city with the smallest number of neighbors at a threshold distance. Leetcode 1334. In this problem, we are given n cities numbered from 0 to n minus 1, and then we are also given an array edges where edges I is equal to from I to I and weighti, which represents a bidirectional and weighted edge between cities from I and to I. And we are also given an integer distance threshold. Then we have to return the city with the smallest number of cities that are reachable through some path and whose distance is at most distance threshold. If there are multiple such cities, we have to return the city with the greater number. Note that the distance of a path connecting cities I to city j is equal to the sum of edges weight along that path. Now they have given some examples as well. For examples, let's switch to light mode. In example 1, we can see that n is equal to 4. So nodes are 0, 1, 2, 3. And now we connect the cities using the edges. For example, for S0, we can connect cities 0 and 1 with weight 3. Similarly, using edge 1, we connect the city 1 and 2 with weight 1. And similarly, we will connect rest of the cities. And then we are also given distance threshold equal to 4. So we can see that we can reach from city 0 to city 1 because distance here is 3. Similarly, we can reach from 0 to city 2 because the distance there will be 4, which is equal to the threshold. So 0 will be connecting to 1 and 2. Similarly, for 1, we can go to city 0 because distance there is 3. We can go to city 2 because distance here is 2. And we can also go to city 3 where the distance is equal to 4. Now we can see that for city 2, we can actually go to city 1, 3, and 0 because the distance here is 1, 1, and 4 respectively. And finally, for city 3, we can actually go to city 1 because distance is equal to 4, which is equal to threshold, and city 2, where distance is 1, which is below the threshold. So this is how we can actually reach out to other cities based on the threshold. So now we have to take the count. So we can see that for city 0, it is 2. For city 1, it is 3. For city 2, it is 3. And for city 3, it is 2. And now we can see that there is a tie between city 0 and city 3 because both of them are connected to 2 cities, which is the minimum number of cities they are connected to. So in case of a tie, we will return the city with the greater number. So in this case, we will return city 3. Now let's jump into the solution space. So there are multiple solutions possible for this problem, but let's rule out the ones which will not work. So one solution can be BFS, but BFS will not work here because BFS works with equally weighted graphs. Now let's try out DFS. And even DFS will not work. Let's look at this graph with n equal to 6, that is number of nodes equal to 6. And suppose our distance threshold is equal to 20. And now we run the DFS, say from node 0. And we try to find out the nodes which are reachable from node 0. And suppose our DFS path was that we went from 0 to 1, and then 1 to 4, and 4 to 5. So in this case, we can see that the sum of the edges is 21. So we cannot reach 5 according to this DFS path. So we will backtrack, right? And find another path. So we will come back to 0 and we try to follow the path in green color, that is 0, 2, 3, 1, 4, and 5, right? So in this case, we can see that our distance is 14, which is less than the threshold distance. But still, we cannot move beyond 1. Why? And the reason for this is this visited set. Because when we actually went with this DFS path, we actually added 1 to our visited set. And because of this, in the green path, when we actually come to 1, the DFS algorithm will see that 1 is already added to the visited set. So it will mark this node as processed. And because of this, we will get an incorrect input that 5 is not reachable from node 0. So now that we have ruled out both DFS and BFS, let's look at this problem closely. So when we are actually finding the city within the threshold distance, we are actually choosing the shortest path. So for example, when we are checking whether 2 is reachable from 0 or not, we are choosing the shortest path. So we are going from this path first and then this path. We are not going like this zigzag way, right? And this is where actually we can either use Dijkstra algorithm or Floyd Warshall algorithm. Dijkstra algorithm is single source shortest path algorithm. What we mean by single source is we actually start from some source node in the graph and find the shortest path from this source node to all the other nodes in the graph. So for example, in this graph, we start the Dijkstra algorithm from node 0, then we will find the shortest path between node 0 and 1, 0 and 2, 0 and 3. And if we have to find now the shortest path between 1 and 2, we have to again run the Dijkstra algorithm from node 1. So what that means is we have to run the Dijkstra algorithm from all the nodes in the graph to find the shortest distance among them. So this is one approach. Another approach can be using the Floyd-Warshall algorithm. And in the current problem, that suits us more because Floyd-Warshall algorithm is all pairs shortest path. So regardless of the source, we will actually calculate the shortest distance between all the city pairs. And this is what is required in this solution. So now let's solve this problem using Floyd-Warshall algorithm. And to understand Floyd-Warshall algorithm, we can take the graph from example 1. So first thing we do in the Floyd-Warshall algorithm is initialize a distance matrix. Distance matrix is very similar to adjacency matrix in the graph, where we actually store the shortest distance between the node pairs I and j. Initially, the shortest distance between the node pairs will be infinite, which in the programming language can be modeled as integer.max value. So for example, the distance between node 0 and 1 is infinite. Similarly, distance between node 0 and 2 is also infinite. But note that the distance to the self is 0. Now we update the shortest distances as per given edges. So for example, we can see that the distance between node 0 and 1 is 3. So we update the distance matrix at 0, 1 to 3 and also at 1, 0 to 3 because it's a bidirectional graph, right? Similarly, for the edge between 1 and 2, we can see that the weight is 1. So we will update the distance between 1 and 2 as 1 and similarly 2 and 1 also as 1. And we continue updating the distances matrix as per the given edges. And after we apply the weights from the edges, now our distance matrix looks like this. Note that we still have some infinites remaining in the graph because we don't have the direct connection between these node pairs. So for example, we can see that there is no direct connection between node 0 and 2 or 0 and 3. So that's why we still have these infinities remaining in the graph. But now we actually go to the next step where we actually start applying the Floyd-Warshall algorithm. And the idea behind Floyd-Warshall algorithm is that we will pick up each node from the graph as an intermediate node, let's call it k, and then update the shortest path between all the pairs of nodes. Let's call them I and j. Let's look at it with example. So initially we will pick k equal to 0. So that means now we will try to make node 0 as an intermediate node between all the pair of nodes and try to update the shortest paths between all the node pairs in the graph. So for example, let's try to make 0 intermediate between node 1 and 2. So for that, we have to first go from node 1 to 0, and then we have to come back from 0 to 1, and then again go to 1 to 2. So that will make the distance equal to 7, right? Which is actually more than initial distance 1. Similarly, 0 will not affect the shortest distance between all the node pairs in the graph. So our distance matrix stays the same for k equal to 0. So now we move to next node, which is k equal to 1. Now let's see 1 as an intermediate node between 0 and 2. So in this case, we can see that our initial distance between 0 and 2 was infinite, right? Because these two nodes were not connected. But now through 1, they are connected. And because of this, the distance between node 0 and node 2 is now 4. That is the distance between node 0 and 1, which is 3, and node 1 and 2, which is 1. So that adds up to 4. So now we will actually update the distance matrix with value 4 for nodes 0 and 2 and 2 and 0. Similarly, now let's look at node 1 as an intermediate between node 0 and 3. And now the distance between node 0 and 3 becomes 7. It was infinite earlier, right? Because distance from 0 to 1 is 3 and 1 to 3 is 4. So when we sum them up, we get 7. And now we save the distance between 0 and 3 as 7 in the distance matrix. Now let's see 1 as an intermediate node between nodes 2 and 3. And now we ask the same question. Does having 1 as an intermediate between 2 and 3 reduces the distance? Let's check it out. So we can see that the distance between 2 and 3 is already 1. But if we try to go from 2 to 3 through 1, then the distance actually increases to 5. That is the distance between 2 and 1, and then 1 and 3, which is 1 plus 4 is equal to 5. So we will discard this distance because we already have a shortest distance equal to 1. And now we are done with the k equal to 1. So we move to k equal to 2. Now 2 is an intermediate node. So we can see that if we try to have 2 as an intermediate node between 0 and 1, that does not help. Next, if we try 2 as an intermediate node between 0 and 3, that actually helps because then the distance between 0 and 3 actually reduces. So it becomes 5 because earlier the distance between 0 and 3 was 7, but now it becomes 3 plus 1 plus 1. So that's why now the distance reduces to 5. So now we will actually update our distance matrix and have 5 as a distance between 0 and 3. Similarly, now let's see 2 as an intermediate between 1 and 3. The distance between node 1 and 3 was 4 earlier, but because of the intermediate node 2, the distance reduces to 2. So we will update the distance matrix between node 1 and 3 equal to 2. And now we go to last node, k equal to 3, and try to have it as an intermediate node between the other node pairs. And we can see that we get no shorter paths if we have 3 as an intermediate node. So now we are done with the Floyd-Warshall algorithm, and we have the distance matrix filled with shortest distance between different nodes in the graph. And now, using this distance matrix, we can actually count the reachable cities within the distance threshold. So for example, for node 0, we can see that we can reach to node 0 and node 1 and 2, because those are the shortest distances which are actually below the distance threshold. So the count here becomes 3. Then we can see that for node 1, we can actually reach all the cities because all the cities have the shortest distance less than equal to distance threshold. So count here becomes 4. Similarly, for node 2, we can see that count is again 4 because we can reach all the cities as all the shortest distances are less than distance threshold. For node 3, count is 3 because we have 3 cities where the shortest distance is actually less than equal to threshold distance. And now we have to pick up the larger values in case of a tie. So we will pick node 3 as an answer. And now we are actually done with our solution. So now let's jump into the code part. So first thing we will do is define the distance matrix. It will be of size n into n. Then we will actually initialize the distance matrix with infinite values. In Java, we can do it with integer.maxValue. Then to fill the arrays, we can actually use arrays.fill function to fill the individual rows. And we can just say dist I equal to 0 because distance to self will be 0, right? Now the next step is we will actually go through edges and update the distance matrix. So our h0 is from, 2 is h1, and weight is h2. So we will now update our distance matrix. Because it's bidirectional, so we will set the weight from 2 and 2 from. Now we will run the Floyd-Warshall algorithm. So now we will pick up the intermediate node as k, which will be between 0 and n. Now we will take the node pair with iterators I and j, such that we use k as an intermediate between I and j and try to reduce the distance between them. So now we have 3 nested nodes. So this should be between I and this should be j. And now we will actually start updating the distance matrix. But before that, we will check if the distance between I and k or j is not infinite. Because if it is infinite, then it will not affect the shortest distance at all. So both the values should not be equal to integer.maxValue. So that's why we have an AND condition. So if none of them is infinite, then we will actually set the distance ij equal to minimum of whatever we have so far, or the distance between I and k plus distance between k and j. And once we do this, our Floyd-Warshall algorithm is complete. So now we have to pick up the city with the minimum reachable city count. So we will set minimum reachable equal to n initially because that is the maximum we can reach. And now we have to find values smaller than this. And let's set our answer city equal to -1 for now. So now we will actually start looping on this distance matrix. Now we will initialize the variable count to actually count the cities which we can actually reach from city I. Now we will check the distance between city I and j using the distance matrix and see if it is less than equal to distance threshold that is given to us. If it is, then we will just increment the count. And once we are done with all the nodes for value I, then we will actually update min reachable. So if we see if count is less than min reachable, then we set min reachable equal to count and answer city is equal to I. But we have to also handle the case for tie. So how we will do is we will use the OR condition and we will see if count is equal to min reachable and I is more than answer, then we will also update the same thing. And once we are done, we will just return the answer. Let's run this code. So we are getting index out of bounds. And the reason for this can be, so I'm looping from k equal to, similarly, I'm looping on I here, and then I'm looping on j. Oh, this should be not I, this should be j. It was a typo. So now let's run this code again. Again, I'm getting index. Oh, okay, the same issue. And let's run this code again. Cool. Let's submit this code. Awesome. In terms of time complexity, it is O of n cube, which is mainly coming from these tree nested loops in the Floyd-Warshall algorithm. Otherwise, when we are actually initializing the distance matrix or updating the distance matrix or calculating the city with the minimum reachable count, that takes O of n square. So overall, the time complexity will be O of n cube. And in terms of space complexity, it will be O of n square, because we are creating this n by n distance matrix and storing all the shortest distance between the city pairs. I hope this video was useful to you. If it was, please like and subscribe. The code link is in the description below. Have a nice time. Thank you.